So I don't think I like fully finished the slides, but it should be okay. So this presentation will be about 2AdicFri in comparison to SimpleFri and like the general Fri protocol. And so just a reminder on like regular Fri and then the SimpleFri, our whole goal was to do low degree testing or ensure a given polynomial is of low degree. This is kind of like the RS thing I showed last time. So if we have a given message, then we can create a polynomial from this message. And in this case, the polynomial is of degree 2, like these 3 points possibly. And then we can add extra evaluations on the same degree polynomial and pass this on to the verifier to be checked. And then so for example, if one of these points is not valid, like shown to be valid by the verifier, it means that the polynomial is like possibly of a higher degree, which invalidates the given code word, this code word. So that's the goal of Fri protocol, low degree testing. SimpleFri protocol, I don't know like how much I should go into this, but as you can see, we have the polynomial. Oops. We evaluate it on a domain, and then we commit the Merkle tree root to the verifier. We get a given challenge back from the verifier, and then we evaluate. We evaluate all of the polynomial. We fold the polynomial and then we evaluate it on another like smaller domain, and then we create a Merkle tree and we commit a Merkle tree root. Keep on folding. The folding part is like commit phase, and then the query phase is where the verifier gives a challenge X, and the prover gives back each a polynomial's f of x and f of negative x, and a Merkle tree proofs for those evaluations. And then the verifier uses all that to verify the Merkle tree proofs and calculate the next layer's f of x. And that's the whole query phase. And oh, another thing I want to mention was, I remember last time Ryan said, I wish that you like kind of combined or explained more on read-Solomon codes in terms of the Fri protocol. So in our case of the SimpleFri protocol, it kind of like our code words are the polynomials or like the evaluations that we commit every layer. And the reason why our Fri protocol does low degree testing is kind of same as what I explained here. Like I explained here, like if a verifier finds a certain value is wrong, it means the polynomial is of high degree, right? So in the same sense, if a verifier finds that one of these evaluations is wrong, it means the polynomial is of high degree. So it's just the verification process that ensures it's low degree. And last time we talked about complexity. Just wanted to put a little bit on it. This still makes me kind of confused, especially the extra number of rounds. So I'll try to go through it. So proof size, this was given by the website that says compared all of these commitment schemes, but it said proof size was O of log squared D, and I think this was gotten by this kind of equation. In our case, it's like the query phase of the prover. So I think they assume that the number of queries is 1, which would like make sense with what I kind of calculated. But assuming no queries is 1, then we'd have log n for creating the Merkle tree proof, and then log Rn of creating the rounds, because each round, the number of rounds is determined by like how much we reduce the polynomial. In our case, it's like by 2 every time. But like there are other cases in the Fri protocol. So that's why they have log squared, I suppose, for this one.
I think we don't have to fix k to 1, because even if k is another constant.
Oh yeah.
Yeah.
I see. Oh, complexity.
Yeah.
Yes. But that's how it works for proof size. And then for proof time, down here it's d log squared d, and this was created by FFT, I think. Is n log n to run, and then creating a Merkle tree is just n to run. So loops total like looping log n times, it creates n log squared n. So that's how this proof time is created. And then for verify time, it's the same, like similar result as proof size. So the num queries is here, and then log n is how much it takes to verify the Merkle tree proof, and then log Rn is again the number of rounds that are run. So that's how complexity works for the Fri protocol. And now we talk about 2AdicFri. So when I was kind of reading through it, I realized it's essentially the Fri protocol or SimpleFri with just a lot of more security added, and then more optimizations, and like a little change in the beginning, and that's pretty much it. So starting with a little change, the 2AdicFri doesn't work with just the original polynomial in terms of folding. It works with the quotient polynomial, a quotient polynomial, which is given here, p of x minus v over x minus z. And this should be a polynomial of degree minus 1, like the original polynomial is degree d minus 1, because, like, for example, if z was a solution, like given an opening plane zv, so this is a solution. If z was a solution, that means our polynomial, like, perfectly is divided by this solution, which should create another polynomial of 1 degree less. And this is what 2AdicFri works on. I'm not exactly sure why they decided to use a quotient polynomial. Maybe it's like for more security, perhaps. But they run it on this polynomial.
Oh, because they want to prove that so PZ is equal to V, because V is given by proof. And in order to make sure PX equals to PZ equals to V, we need to prove with quotient.
Yeah. Okay. And yeah. So in terms of our code, actually, we had like commit and then create opening proof and verify opening proof in this SimpleFri protocol, SimpleFri. But in 2AdicFri, we also have the same, but the way they coincide in terms of the Fri protocol, the commit function on 2AdicFri commits the evaluations on a domain, like the original evaluations on the way I kind of did it. Get this right for which one was this one. So this is the original 2AdicFri setup. The commit on our side is this commit right here. The polynomials evaluations on the domain. This is what is like initially sent for 2AdicFri, and it's not part of the commit phase of the Fri protocol. The Fri protocol that we use in 2AdicFri is just like for this guy only. Going back. Yeah. This slide just essentially says that the Fri protocol is exactly the same done on 2AdicFri and SimpleFri, except the polynomial that is implemented is different. So given this polynomial, we evaluate on a given domain, we create a Merkle tree, commit the Merkle tree roots, and then fold using challenge B, and then keep on looping until we get the final evaluation constant. So it's the exact same as SimpleFri, and the current phase also works the exact same.
But here I found the final UVR is not a constant. It's a polynomial that has a degree, because they don't even go up to the most top because there's broad factor. So we don't have, because what we want to prove is that the given polynomial is have degree less than some certain d.
Yes.
So we don't have to deal with the extension protocol, because the leaves are extended to like 2 times or 4 times or 8 times, right?
Yeah.
Even you don't have to go up to like d plus 3 height. You can end at d height.
I see. So since the original evaluations have been extended,
Yeah.
the final eval we get isn't supposed to be a constant. It's supposed to be a polynomial.
Yeah.
Because like we
2 or 4 or 8.
Okay.
Depending on broad factor.
Cool. But yeah, the query phase is also the same, where the verifier checks everything using like the beta and like all the linear combination values to create the next evaluation. So that's like all the same. The big differences about TwoAdicFri is in terms of soundness security and reducing proof size. So there's a couple of big differences. Let's start like extension field, blow factor, non-queries, bit reversal, combining polynomials, and how it is. So start with extension field. I'm gonna go off on what Ryan showed me in his explanation of the protocol. But this is what I mentioned earlier of the commits of the polynomial evaluation of the polynomial on a certain domain, and that's committed initially in TwoAdicFri. And this is done in our like the values of this are just regular field values, but the results of this are zeta, and then these values are all extension fields. And the reason why this is done is because our evaluation domain size is like 2 for given like baby bear, it would be like 2 to the 27, and then our field size for baby bear would be 2 to the 31, and this chance, like putting evaluation domain size over field size, is a chance of the verifier missing a faulty value. So we want to increase this value and help the verifier have a better chance. I might have to mess this up a little bit, but we want to ensure that it's secure enough. To do that, we increase the value of the bottom, our denominator, our field size. And the way we do this is by using quadratic extension fields instead. So we use baby bear 4, and this means that the field size is multiplied by 4. Yeah. Yes. Quadratic. And if it's multiplied by 4, then you can see here that the chance goes down to like 1 over 2 to the 97, which is massive difference. And this is why extension field is used. The next thing we have that's interesting in TwoAdicFri is the blowout factor. So this is used for coset LDEs, our initial evaluations of a polynomial on the domain, like this guy right here. It's used to blow up the number of evaluations in total. And the reason we do this is because we want to maintain security. If this wasn't done, it's possible that the polynomials could be leaked through queries. So that's why we have these blow factors. And if you can see here, I kind of drew something right here when I was figuring out coset LDE batch. It's like the blow factor of 1. Every blow factor is like 2 to the blow factor. That's the new domain is. So this is the original evaluations on the domain, and then the blow factor increased it to 2 times. And the evaluations are now 2 times the amount. And so blow factor.
Maybe it reminds me of this extension over the flag.
Do you have any idea why proof size is smaller and higher blow?
Higher blow factor reduce the proof size.
Yeah.
In the
right side.
I think this is because of the number of query reduced. Sorry?
Number of queries is same, no?
No, it's reduced because if you go to the slides I give you.
This one?
No, in the slide. Yeah. And let's go to 29 and 13. Page 29 and 13.
29.
Yes. So if you don't have a extended, if there's a 130 value out of 10 value, in order to detect whether it's good or vary on now with just random sampling, you need to the possibility to detect invariantly is something like in this table. So you need to query even though you query 9, the possibility is just 0.61. If you go to search page, if you use ratio code, then if you sampling 7 times, they almost detectable. Yes, so
yeah, so load factor is one of the values used in to increase security in TwoAdicFri. Yeah.
Is there like 10 values just randomly filled?
yeah. So the left arrow means it samples from challenger. Like here.
Yeah. The next thing TwoAdicFri is same thing, like num queries. So it's a number of total queries that verifier asks for. Like in our case from before, we had like 1 to the 97 chance. Did I like do this one? No. Okay. Yeah, this is right. So this is a chance that the malicious prover with a faulty value succeeds. And so I made a slower example. So this is a sample where you have a 1 out of 4 to the query number chance of a malicious
I
prover.
think this is actually can, because that means if you use this expression, if you query many times, we can achieve the security bit.
Yeah.
So we need to use different equation regarding query number. And they used to say that return code is always related to some delta distance in order to make sure. So the code word can have so they use what is the distance matrix?
Having distance?
Yeah, they use Hamilton distance. So in the entire code words, there can be delta invariant something. So you need to use this expression in this way: 1 minus delta.
1 minus.
Oh, no. 1 minus delta to the q.
Q?
No, 1 over 2 to the 97 should be changed.
1 minus
Delta. Oh. Yeah. So this only works for the first iteration. After the second iteration, the equation changed. Like now it only works for first and the second rate to the q. Yeah, because but the ChatGPT state, or I don't know where it was from after second iteration. Because after the 4D polynomial, in order to be low degree polynomial, the chance to deceive the verifier is as same as rate, because there's only there's a the denominator in rate is core version domain, which is extended. But in order to make the polynomial low degree polynomial, there's only d case. So if we fix d, then rate the q is the one that we have to use.
Okay. Well,
yeah. There's the.
I think this shows more exactly what.
Yeah.
I tried to show, but okay, we'll just skip this past this part. There's also another thing I found in an article by Lambda class, which I think was pretty nice to me. There's a trade-off between blow-up factor use and the number of queries. So you guys kind of mentioned it earlier. So blow-up factor increases proof work and memory use, and number of queries increases proof size and verifier work. So the next thing let's talk about was bit reversal. This happens a lot within TwoAdicFri, and one of the main reasons for it was like memory storage and how we could store values that will be used together in the future, like right next to each other. So in our SimpleFri protocol, if you remember, like back then, I talked about evals and eval sim, which is fx and f of negative x. This is what we use to verify queries and then uses to verify all of the evaluations. And for creating f of negative x, it was adding half of the domain size, right? And the way we can make these two index values right next to each other is by doing bit reversal. So like if we look at this kind of domain, we would have to, like, for example, if we had evals of 0, then eval sim would be 4. So we'd have to like add exactly half of the domain size. But if we do bit reversal, so get the bits and then you like reverse it on like a mirror, right? Then you have 0, 4, 2, 6, 1, 5, 3, 7, which means that the values that are needed to be used together are right next to each other. And this is used a lot in TwoAdicFri, specifically for this purpose. Okay. Next thing is multiple polynomial inputs. For SimpleFri and like what the general Fri protocol talks about, they accept only a single polynomial, which is a vector of dense coefficients. But for TwoAdicFri and specifically our use of it, we accept a number of polynomials, so a lot of polynomials of various degrees. And this turns out to be a vector of matrices. So I have this guy. So a vector of matrices, such like this, where each matrix would be polynomials of a certain degree. So all these polynomials are of, what is this, degree 8, 7? And then this one is 3, and then 1. That's kind of weird, but this is how the matrix of vector matrices of the polynomials would work.
Oh, I think matrix of polynomials in evaluation form, I think.
Oh, for the
Yeah.
And one thing that TwoAdicFri does to optimize this is combining the polynomials with linear combination. This is also called batch-fri, I think, in online explanations. So if we ran each polynomial separately on the Fri protocol, this would result in a Merkle tree for each polynomial and separate Merkle tree proofs for each polynomial on each layer, which is a lot of expensive cost. To solve this, we create one Merkle tree with linearly combined polynomial evaluations. So for example, if these are the evaluations of these separate polynomials, then we would linearly combine it with some random value, such like this, and run the Fri protocol using these evaluations. So like this would be a leaf and this would be a leaf. Meanwhile, in these, if we did separately, this would be a leaf and this would be a leaf. It's all combined together. And so if we do it this way, and then we get a faulty value from our verifier while running this, it just means that like maybe one of the polynomials is wrong or all of them are wrong. We don't know, but it automatically just says it's wrong. And so it works in that way.
As far as I remember, if there's a polynomial that has a different degree, still it combines, right? It's combined to these of the highest degree that this polynomial has.
I'm not sure, but I suppose that would work. But we only work with polynomials of the same degree within the matrices.
In SQ1?
in Fri, yeah, I believe.
But the code itself can handle a different degree, but maybe it has kind of extension of this explanation, so you can skip and everyone can go to see code later.
Yeah. This random thing on the side, this random value for linear combination was also explained by Ryan in this protocol. We get a zeta here from these commits, but we also get an alpha. And this alpha is used to linearly combine all these polynomials evaluations. So this is batch try. The next thing we have is POW witness. I actually researched a little more on this. So what this paper right here was talking about by the Starboard team told me that the POW witness increases the cost of being a malicious prover, and it reduces the number of queries needed to be done by the verifier. And what it does is has a 64-bit nonce that when hashed together with the state of the hash chain results in a required number of leading zeros that follows all the commitments made by the prover. As you can see here in this protocol, in the final eval, after the final eval, we also commit the POW witness. So it's done after all the commitments.
Yeah, and also it has to, because there's some library on G, which is 120.
It was like 112 or something.
And if you add like 97 plus then if you add because the chance yeah, we need to assume that the hash is kind of pseudo-random function.
Yeah.
Then the possibility to make the least significant 16-bit zero is like 2 to the 16 over 2 to the 31, which is 2 to the 15. And if you add 15 plus 97, it was 97. Yeah, then that was 60 level.
It was like 113 when we calculated it. But it's close enough.
Yeah.
Something is wrong, but
Yeah.
So
yeah, that is so. I actually read the code from Stir, and that's exactly saying they calculate the POW witness bits. Yeah, so it's
Maybe implementation. I mean, the Plonky3s. Maybe they actually want 113 bits of security in their implementation.
No. It's just calculation from our paperwork. So maybe there's some mistake. And that 16 security bit actually is by SQ1 attacking.
Oh yeah.
Yeah.
SQ1. So this pretty much means that an honest prover only needs to create, I think it's like create this 64-bit nonce that when hashed together with everything creates the number of zeros once, but a dishonest prover has to keep on creating this nonce every time a commit is changed. So it's just way more taxing for a malicious prover.
And I think it's important to mention that the reason why we multiply 97 1 over 2 to the 97 times 1 over 2 to the 15 is because it uses observe. So whenever we come into some polynomial, we touches the state inside of Poseidon 2, and based on this, we calculate proof of work. This is why it multiplies those terms together.
It was 2 to the 15 divided by 2 to the 31 was 2 to the.
Oh, what's 1 over 6?
Yeah, that's true.
Wait.
1 over 1 over.
1 over.
I mean,
yeah, 1 over. Yeah. 1 over 2 to the 16. And then given our 1 over 2 to the 97. Oops. multiplied by 1 over 2 to the 16.
Now 13.
1 over 2 to the
Yeah, that's how we convert. Yeah.
Yeah. And then I kind of included here the protocol. Should we go into it? I think it's pretty much.
노하우 질문 있으세요?
네?
질문 혹시 있으세요?
아니요, 없어요.
I think this is like pretty much most all of the main features that TwoAdicFri does that SimpleFri doesn't do. You can kind of see the protocol here. It's just like we commit all the evaluations of the polynomial on the domain. In our case, it's TwoAdicFri. It's done on a coset with LDE, which just means like the log blow factor is included in that. And then we get the zeta back, this value for which we evaluate the polynomials on that value, and then create these commitments with the quotient polynomial. Create the commitments of the quotient polynomial. So the quotient polynomial we use to create evaluations on the domain again. This is sent as commits to the verifier, and then we get this beta, which is used to fold. The fold process happens up here. And then we get the final evaluation and the power witness, and we query.
This is index of the
Challenge. Yes. The
opens.
yes. We get the index of the opening that we want to like challenge on, and we send these proof. Wait. The evaluation of the polynomial on the unity of that index and the proof, and then the same quotient polynomial with that index and the proof. And then the query phase happens, which is like the same in SimpleFri. So
yeah, and I think it's also good to mention that the reason why we evaluate P of C, but we cannot produce the opening proof for that because the domain is out of domain. The sample alpha is out of domain, which is yeah.
okay.
So the one more. So it actually used the same in star. So in order to sample out of domain thing, you can just use sample in Challenger. But if you want to sample within the domain, you need to get the index. So like modular, like using modular operation. You have mode by domain style.
Yeah. And the next slides are pretty much just comparing SimpleFri to the
How about also mentioning why do they use coset domain?
I think that was just for six.
Oh yeah. It's good to mention, but
I don't know if I have a slide. I don't think I have a slide. Oh, no,
then it just work.
I think that's related to kind of extension field.
Yeah, maybe in paper. Yeah. Yeah.
Yes. So we used coset LDE for the first commits of the evaluation of the polynomial, and it's just for security because the queries could possibly leak the polynomial itself. So a coset is needed to be used to prevent any of that information being leaked.
Yeah, because we open some point at index within domain. That means you need to open one of these
Yeah, so like it can't be the original polynomial values.
yeah.
It has to be like some different
Yeah,
values.
yeah.
I think that's like, wait. These two last slides were pretty much kind of reiterating what I said earlier. It's just that in SimpleFri we have a polynomial and we evaluate on the domain with this polynomial and we commit the Merkle-Tree root before commit phase. But for 2AdicFri, we like do all this stuff and gain the quotient polynomial instead, and then we run the commit phase and the query phase on this polynomial. But besides that, like the protocols are like pretty similar. Besides like security and extra case. Yeah. So also here, it's like during the query phase, they receive a challenger, it commits these two, and SimpleFri commits both Merkle-Tree proofs for every layer, but 2AdicFri just commits one Merkle-Tree proof because of bit reversal. We have the evaluations right next to each other, so we use that as one leaf, and we can just get a Merkle-Tree proof for that one leaf. So they're like similar in every other way though. And 2AdicFri also has inquiry phase for the verifier checking the PAL witness, and that's like the main difference as well. I think that's like it of what I wanted to explain. This is all like deprecated slides. Yeah.
What about showing how to evaluate C based on domain, because in the protocol it's less like
No, it's okay.
yes. In anyway, we need to compute P of C based on P over some domain, and it would be nice to show us how to compute P of C using this. Maybe.
I don't know if this is exactly.
What about showing that with the that's like go down. Yeah.
Is it this one?
No. Next page maybe. Oh yeah, that one.
Ryan has graciously created these slides for me. But from these evaluations on like cosets, how do we get the original PMZ? We create the polynomial like P of X by using these values and getting the Lagrange terms, right? The Lagrange polynomials, and it's pretty much interpolation and like eccentric interpolation. Get the value in the Lagrange terms and create a full polynomial. And this is just showing what the Lagrange terms, Lagrange polynomials are. But it's like x minus all other values on top, x minus value, and then all those multiplied except for the original one on top, and then the bottom one is like what is it? The value, the terms value minus all the other values on bottom. So that's how that's what a Lagrange term is. And when we do this, we can interpolate and create a polynomial. Why not?
So verifier does all this, right?
Yeah.
Verifier PC computing PC.
Yeah.
No. Prover does.
For the next layer. Wait.
No. PC is the opening value from the original market tree, right?
But then why just not? I mean, the prover already knows P, so why not just calculate PC? Why do we have to do Lagrange?
Because it's out of domain, and we only have a polynomial in evaluation form. If it is a coefficient form, it's simple.
Oh, I see what you mean.
Yeah.
So these are the evaluations of the polynomial on a coset, which are these guys. Wait, but the polynomial does have the original.
Yeah, they don't want to, because we want just one evaluation value. So we want to avoid IFFT because it involves n log n operation. And they don't want to do this for performance.
I see.
What we need just some evaluation value at some point zeta, or there's only actually two opening point in epsilon, zeta and omega zeta.
Mhm.
And they want to just compute evaluation.
Okay, but like this is the polynomials evaluations on like a coset domain, right?
Yeah.
And then this would be just the evaluation of a polynomial on a value, original polynomial on the value, right?
Yeah, but the G belongs to
Extension field.
Yeah.
I see. Okay. Yeah. This portion is like from these values how we get these right by the prover. Yeah. So through interpolation and Lagrange polynomials, we can we can get the evaluations and turn them into the value on a given other challenge that we get, which is done here.
Also, you need to go to the next slide. So this was because before previous slide, so PG is actually evaluates PX at C, but we don't know, we can't compute R at this moment wisely. So we need, in order to identify what R Lagrange polynomial is, we need to go to the next slide. And if the I is 1 over like C, if it's so, D0, there's a pattern like if and D0, because omega square, if omega square is 1, that means omega is -1. If we replace omega with -1, it will be 1 over 2z. And if n is 4, then pattern is used. And the 4 is 1, that means omega square is -1. If you keep doing and doing that, yeah,
You get this.
yeah. Now we can compute it. So because next slide, there's some polynomial that combines all together. So large polynomial looks like that. Now we can compute PC. And from the verifier perspective, in order to ensure that PZ is that value, they need to verify some Markov proof in the last section of the proof.
Merkle tree,
Yeah.
the further coordinates.
And from the prover perspective, they need to prove that PC is actually P evaluation of C. Yeah, and then verifier can evaluate all things outside of open, because there must be some constraint like commutation also has their own constraint, and custom gate also has its own constraint, and we need to evaluate z or omega z using those opening values. They can ensure that all these are 0. Now that proof is very.
You say all these are 0.
I mean, like if you go to header to boot, you check the computation argument. Like if you go down, in order to computation is maybe it's in the left bottom. That should be 0, right? Yeah, all these 4 should be 0. And in order to evaluate this at random point, which is Z, or because of the omega x, we need also omega zeta. So if there's a Z and omega Z of open value, we can compute all, and if all those evaluations are 0, then we can trust the proof. So also, if you take a look at the code in Plonky3, there's a lot of things to make us confused because there's a four-dimensional vector and yeah,
It's actually also tech.
yeah. So it would be nice to explain why it is four-dimensional vector.
Oh, I can do that.
Yeah.
So these open values, I actually did here. So they're the ZV that we opening claims of like all the queries we want. All the queries. Yeah. And so we get the Z's, but we need to create the V's, which are the open values. And this we do through interpolation. The way the polynomials are inputted are as a vector of matrices. So this, for example, like this would be one polynomial, blah, 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 and it's a vector of these different, they should be different degrees, so different number of rows, but like I kind of didn't put that there. And we have given points that we want to evaluate these polynomials on. So these kind of points, I believe, with these values, and it's like the same thing. We use interpolation with our evaluations and our given point, and we create our open value final evaluations. And that final evaluation would be a vector of extension fields because it's like more than one polynomial. So this will be like f of 0 on this point, and then this will be f of 1 on this point, and this will be f of 2 on this point. So that's
actually there's like double vector because opening point can be vector.
Oh,
because there's a zeta and omega zeta.
okay.
So
these individual evaluations are vectors of vectors of extension fields.
Yeah.
That makes more sense. And it's the open values here would be vectors of extension fields, and then if you look on a higher at a higher view, it's a vector of a vector of extension fields, and then given the number of matrices you have, it's also a vector of extension fields. So that's why we have this like really crazy.
And because of that crazy structure, the code is actually really hard to read.
Yeah, like they keep on looping through a lot of things that are like really confusing.
So even combining, anyway, you need to combine all polynomials in single polynomial, right? That is actually p power or something. That is very hard to read.
Yep. Any other things to talk about? Nope. It is 퇴근 시간.
이 그냥 제너럴 프라이가 플롱키3 프라이냐?
This one right here, TwoAdicFri, the one with Disney, or
둘다 있는 거 아니지? Plonky3.
yeah, they have naive and TwoAdicFri, but specifically for like our benchmarking, we use TwoAdicFri because that's the more like actual protocol use.
액션 프로토콜이 플롱키3 있냐?
네, 둘 다 있어.
아, 둘다 있구나.
I think it's called like naive in this. Naive.
그게 너무 다르구나.
I don't know if this is the right one, but TCS.
그러면 심플프라이가 어디 있는 거다? 레퍼런스 결과적으로 레퍼런스가 좀 있었으면 우리한테 좋았겠다. 심플프라이는 플롱키3 있는 건가? 아이폰 이거
Tachyon. Ooh.
나 이게 좀 심플하게 어디 있어?
들고 있는 거예요? 람다웍스
Lambda works. Yeah, I think Plonky3 just has TwoAdicFri, actually.
But the SimpleFri actually, so I read the post of Star, which is the paper that got best paper reward at crypto 2024, and they implement it exactly same as the SimpleFri. They implement SimpleFri way.
I feel like that's not that secure.
크립토는 진짜 엄청난 하나인데 하나님과 전화를 보내. 그래서 베스트는
그렇게 말하니까
씹어 먹는 건데.
그래서
크립토 이렇게부터
크립토 2024 크립토.
크립토. 근데 크립토 갖고 있는 그다음에 학회를 짤까?
유로 크립토가 엄청 큰가 보네요.
유로 크립토 시작했습니다. 유로 크립토.
이런데 아직 유럽이 없는 크립토 2024 한번인가?
SimpleFri. Naive was for FTs.
수고하셨습니다. 내일부터는 같이 시작하고
Nice. Bye no.
혹시 너가 질문
수고하셨습니다.
Oh,
아니요, 없습니다.
안녕하세요.
수고하셨습니다.
어,